Welcome, curious minds, to the deep dive. You might be holding a pretty powerful computer right there in your hand. It feels fast, it's slick, it does incredible things.
Yeah, amazing what fits in our pockets now.
Totally. But what does fastest truly mean in the world of computing? I mean, can you even begin to imagine the sheer ambition, the staggering scale behind building the world's fastest machine at any given point in history?
It's a mind-boggling concept, isn't it?
Today, we're not just thinking about speed in the abstract. We're diving headfirst into the fascinating, sometimes really intricate, and often quite secretive history of supercomputing.
It's a journey that really traces the very edge of human innovation. It's a story, of relentless competition, fierce rivalries, and this constant redefinition of what we even think is technologically possible.
Right.
These are the colossal machines that have quite literally shaped our world. They've influenced everything from, well, wartime strategy to climate prediction and even the very foundations of artificial intelligence.
Absolutely. And this deep dive, it's built upon a really rich collection of sources. Primarily, we're looking at a profound lecture titled A History of Supercomputing by the brilliant Burton Smith.
A legend in the field.
Definitely.
Yeah.
And we've supplemented that with material from ECE 8443 pattern recognition and also the essential Getting Up to Speed, the future of supercomputing.
So our mission today is pretty comprehensive. We're going to unpack the foundational definitions that sort of govern this elite field. We'll trace the extraordinary lineage of these giants, from their secret wartime origins right through to their complex, networked modern forms. We'll explore the pivotal architectural shifts, the big ideas that shape their development, and maybe even peer into the future a bit, see what lies ahead, understand the challenges, the opportunities on the horizon.
That's right. This deep dive is really designed to give you a shortcut, kind of a rapid immersion into truly understanding these behemoths that underpin so much of our technological world. And prepare for some genuine aha moments, because we're going to connect these seemingly abstract technical concepts to very real-world challenges, breakthroughs that have impacted all of us, directly or indirectly.
Yeah, the connections are often surprising.
So let's start right at the very beginning. When we talk about a supercomputer, what are we actually, talking about? My first thought is simply the world's fastest computer at the time. But that feels almost too simple, doesn't it?
It's the most basic starting point, yeah, and maybe incredibly crucial for that reason, but it is deceptive in its simplicity. What's truly fascinating here is that fastest it's not a static target.
Right.
It's a moving, constantly evolving benchmark.
Yeah.
The machine we call fastest today will be, well, easily surpassed tomorrow, or maybe next year.
Okay.
Think about it. In the 1940s, fastest might have meant finishing a complex calculation in, say, hours instead of days. Today, we're talking quadrillions of operations per second, petaflops, exaflops.
Mind-boggling numbers.
Exactly. So the definition is entirely context-dependent. It shifts as technology advances, as new benchmarks emerge, and critically, as the sheer scale and complexity of the problems we want to solve just demand more and more computational power.
So it's driven by the problems, too.
Absolutely. It's no longer just about raw clock speed, how fast the processor ticks. It's about how effectively a machine can handle specific, often highly parallel, complex workloads. Things involving vast amounts of data or incredibly intricate simulations.
Like weather forecasting
or simulating nuclear reactions, designing drugs, training huge AI models. Yeah. It's really about being at the absolute frontier of computational capability, whatever that frontier looks like at that particular moment.
Okay, so it's relative. Always pushing the envelope. Now, to
That's
truly appreciate how these architectural giants evolved, we need to understand some of the fundamental language, the language of speed they were built on.
The building blocks.
Exactly. That brings us to some key architectural concepts. Let's maybe unpack the distinction between SIMD and MIMD.
Yeah.
For those of us trying to visualize this, could you give us an analogy for SIMD?
Okay, sure. SIMD. It stands for Single Instruction Stream, Multiple Data Stream. So you can think of it like a highly disciplined, synchronized swimming team.
Okay, like that.
The coach, that's the single instruction, shouts, "Execute a perfect backflip."
Right.
And every swimmer who represents a processing element executes that exact same instruction simultaneously.
Got it. All doing the same thing.
But here's the key. Each swimmer is doing that backflip in their own section of the pool. They're working with their own unique set of data, their own water, if you like.
Ah, okay. Same action, different data.
Precisely. So one instruction, but it's applying, of course, this whole array of different data points. This architecture is incredibly efficient when you have the exact same operation to perform on a massive data set. Think image processing, like applying a filter to every single pixel.
Right. Same filter, millions of pixels.
Exactly. Or doing vector calculations, where every element in a big vector needs the same mathematical operation. Very powerful for those kinds of tasks.
Okay, that makes sense. So if SIMD is the synchronized swimming team, all in lockstep, IMD must be a very different kind of performance. IMD stands for multiple instruction stream, multiple data stream. What's a good way to picture that one?
Well, sticking with the performance theme, your analogy of an orchestra is pretty much perfect for IMD.
Right.
Multiple instruction stream, multiple data stream.
Okay.
Here you've got many different sections, strings, brass, percussion, woodwinds. Each might have its own conductor, or maybe they're just playing from their own unique sheet music.
Different parts, different notes.
Exactly. Each section, acting like an independent processor, can be doing its own entirely different task at the same time, asynchronously.
Yeah.
You know, the flutes might be playing a melody, the drums doing a complex rhythm, the violins playing a harmony.
All contributing to the whole piece.
Right, but they're independently executing their own instructions on their own data. This distinction is absolutely crucial for understanding how designers have scaled performance over the decades, because MIMD allows for much greater flexibility and general-purpose parallel processing.
Ah, not just lockstep operations.
Correct. It can tackle problems where the tasks are diverse and independent, not just the same operation on different data. This makes it suitable for a much broader range of complex applications. It's really the dominant paradigm today for that reason.
I see. So the nature of the computation, the problem you're trying to solve, really dictates which approach might be more suitable, or maybe a mix.
Sometimes, yeah. Modern systems can be complex, but beyond the instruction stream, how the data is accessed by all those processors is also fundamental. You mentioned shared memory, where there's a common memory accessible by all processors.
Like one big whiteboard everyone can write on.
That's a good way to think about it. But then there are important distinctions within that shared memory idea. UMA, uniform memory access, and NUMA, non-uniform memory access. Can you clarify those for us?
Sure. So shared memory, like you said, conceptually, it offered a simpler programming model initially because all the data was notionally in one global address space. Any processor could see any piece of data.
Sounds easy.
Well, UMA, or uniform memory access, is the sort of ideal scenario. It means every processor truly sees and accesses every piece of memory with the exact same latency, the same access time, like at every spot on that whiteboard is equally easy to reach for everyone.
Okay.
This is fantastic for programming because you don't really have to worry about where the data physically resides.
Yeah.
The system handles it. However, implementing true UMA becomes incredibly complex and expensive as you add more and more processors.
Why is that?
Because you need an incredibly fast, wide, and totally bottleneck-free pathway connecting all the processors to all the memory. It simply doesn't scale well to very large systems. The traffic jam gets too big.
Ah, the bottleneck problem. Okay.
Yeah. So NUMA, or non-uniform memory access, emerged as a more practical and, I guess, necessary compromise for larger shared memory systems. With UMA, the system's total memory is physically distributed across different nodes.
Nodes?
Yeah, think of them as neighborhoods. Each node typically contains one or more processors and a chunk of the total memory. Now, a processor can still access any memory in the whole system.
So it's still shared?
Conceptually, yes.
Yeah.
But accessing memory that's on its own local node, its own neighborhood, is much faster than accessing memory on a remote node, which requires going across the interconnect network, the highway between neighborhoods.
Ah, so access time varies, non-uniform.
Exactly. That variation in access time is why it's non-uniform.
Oh.
And it poses a significant challenge for programmers and compilers. They really have to strategically place data in memory as close as possible to the processors that will use it most often. Otherwise, performance just tanks.
So it puts the burden back on the software side.
Pretty much. It's a trade-off between the conceptual simplicity of shared memory and the physical reality of building large systems. UMA is ideal, but hard to scale. UMA works better at scale, but needs smarter software.
Got it. And then there's the other big approach, distributed memory. Your analogy was everyone having their own notebook and passing messages back and forth. Is that about right?
That's a perfect analogy, yeah.
Yeah.
In distributed memory systems, the memory is explicitly partitioned into regions that are private to each processor. Each processor has its own local memory, its own notebook, and it can only directly access that.
So no shared whiteboard at all?
Nope. If a processor needs data that's in another processor's notebook, it has to explicitly send a message, like passing a note, requesting that data, and the other processor has to explicitly send it back.
Message passing.
That's the key. Communication between processors happens solely through this message passing mechanism. This model fundamentally changes how you think about data management and access.
What's the advantage then? Sounds more complicated.
The huge advantage is scalability, because you avoid that single central memory bus bottleneck that can just get saturated in shared memory systems as you add more processors. You're not all trying to access the same central resource.
Avoids the traffic jam again.
But as you guessed, it places a much heavier burden on the programmer. You have to explicitly manage all that communication, deciding precisely when and how data needs to be sent and received between processors.
So the network connecting them becomes crucial.
Absolutely paramount. The efficiency and speed of that interconnection network between all those notebooks is everything in these systems. It's the dominant architecture for the biggest supercomputers today because it scales so well, even though it's harder to program.
Okay, clear trade-offs there. Now, moving briefly to the chip design itself, we heard about RISC versus CISC. RISC, Reduced Instruction Set Computer, uses fast, simple instructions to do complex things. That sounds a bit counterintuitive for speed, doesn't it?
It does at first glance, yeah. But it was actually a profound realization that truly transformed processor design. The lecture notes you mentioned highlight this key idea. It was better to make the instruction set simple if you wanted the chip to run fast.
Simple equals fast. How?
Well, the logic is pretty elegant. Think about CISC, complex instruction set computers. They might have a single instruction that does something really intricate, like multiply two numbers and then store the result in memory, all in one go.
Seems efficient, software-wise.
From a software perspective, maybe, but that single complex instruction requires many internal steps within the processor to execute. That slows it down, it complicates the hardware design, makes it bigger, uses more power.
Okay.
RISC, on the other hand, breaks down that complex task into lots of simpler individual instructions, like one instruction to load value A, one to load value B, one to multiply them, one to store the result.
More instructions, though.
Yes, technically more instructions to write the same function in code. But here's the trick. Each of those simple instructions can be designed to execute extremely quickly and efficiently, often in just a single clock cycle.
Simpler hardware for each instruction.
Exactly. By simplifying the instruction set, designers can create faster, more streamlined, more power-efficient circuits for each basic operation. This allows the chip to execute many more simple instructions per second, leading to higher overall performance, even if a complex task technically requires more individual instructions to complete.
So it's about throughput of simple steps versus complexity of single steps.
Precisely. It was a shift from doing more with one instruction to doing many simple instructions very, very fast. A key insight.
Got it. And finally, before we hit the history, let's talk about pipelining. You mentioned it earlier. I always think of this as processing in an assembly line style. Is that fair?
That's a perfect analogy, and it's absolutely critical for modern processor speed. Think about a car assembly line, right? Instead of one worker building an entire car from start to finish, which would be incredibly slow.
Takes forever.
Different workers perform different stages simultaneously on different cars. One worker attaches the chassis to car A, while another is installing the engine in car B, and a third is painting car C, all at the same time.
Okay, parallel stages.
Exactly. In computing, an instruction typically goes through several stages: fetch the instruction from memory, decode what it means, execute the operation, and then write the result back. Pipelining allows these stages to overlap for different instructions.
So while one instruction is executing,
the next instruction can already be in its decode phase, and the one after that is being fetched from memory. It creates this continuous flow like the assembly line. Theoretically, in an ideal pipeline, you complete one instruction per clock cycle, even though each individual instruction still takes multiple cycles to go through all its stages.
Huge speed up potential.
Tremendous efficiency gain. But, and this is a big but, it comes with significant pressure on the compilers, the software that translates high-level code into machine instructions.
Why the compilers?
Because the compiler has to be really smart about strategically reordering and optimizing the instructions to keep that pipeline full and flowing smoothly. It needs to avoid stalls or bubbles where the pipeline have to pause and wait, maybe because one instruction needs the result of a previous one that isn't ready yet. These stalls drastically reduce performance.
So it's a high-stakes game of timing and coordination for the compiler.
Absolutely. Keeping that computational assembly line running without hiccups is key.
Okay, great foundational concepts. Now, before we dive into the actual machines themselves, it's probably worth getting to know some of the key players, maybe not people, but the institutions driving the demand. We'll hear these acronyms quite a bit, right?
Yeah, definitely. There's BMD-ATC, that's the Ballistic Missile Defense Advanced Technology Center in Huntsville, Alabama. Crucial for defense. Then BRL, the Ballistics Research Laboratory in Maryland, now part of the Army Research Lab. Think artillery, weapons calculations.
Got it.
DARPA, of course, the Defense Advanced Research Projects Agency. They funded a lot of this cutting-edge stuff.
A blue sky research arm?
Exactly. Then NASA Ames and NASA Goddard, the space agency's big research centers. Huge computational needs for aerodynamics, space missions, Earth science.
Makes sense.
And finally, the national labs, the big guns. Livermore, Lawrence Livermore National Lab, Los Alamos National Lab, the NSA, National Security Agency, and Sandia National Laboratories.
These institutions are absolutely crucial to the story, aren't they? Because they represent the absolute cutting edge of national defense, scientific research, intelligence gathering. Their incredibly demanding applications were the primary engines driving this relentless quest for faster and more powerful computers.
It wasn't just academic curiosity.
Not at all. Whether it was simulating the incredibly complex physics of nuclear reactions for weapons design or stockpile stewardship, or designing complex aerodynamics for spacecraft, or precisely tracking ballistic missiles for defense, or breaking encrypted enemy codes to gain strategic advantage. These were urgent, often existential needs.
Right. Real-world imperatives.
Exactly. Without their specific, high-stakes, and often incredibly complex challenges, the development of supercomputing as we know it probably would have taken a very different path. Maybe much slower, maybe focused differently. Their unique problems often force engineers to invent entirely new computational paradigms just to get the answers they needed.
So these foundational terms, the architectures and the institutions, they're truly the key to unlocking the story of how these behemoths were built and, maybe more importantly, why they mattered so profoundly.
Couldn't have said it better. They set the stage.
Okay, let's journey back now to the very early days. The origins of supercomputing are just deeply intertwined with global conflicts and national security needs. We really have to start with Colossus, the secret code breaker of World War II.
An amazing story.
It was famously used at Bletchley Park in England, right? For cryptanalysis of the German Lorenz SC4042 rotor systems, the high-level stuff the British codebreakers nicknamed FISH.
Yeah, incredibly high-level communications. Much tougher than Enigma.
Can you imagine the secrecy, the sheer scale of the operation, and just the potential heat generated by those, 2,400 vacuum tubes in the Mark II, working around the clock in a wartime environment?
It is hard to fathom, and the fact this machine was only recently declassified by Her Majesty's government, decades later, really underscores its strategic importance and just how deep the secrets it held were.
Absolutely. Tell us a bit more about Colossus itself.
Well, it was truly a marvel of its time, born directly out of that urgent wartime necessity to intercept and decrypt German high-level military communications. Its conceptual framework was largely laid out by the brilliant mathematician Max Newman and his team at Bletchley.
But the engineering was key.
Oh, completely. The actual design and construction were led by Tommy Flowers at the Post Office Research Station in Dollis Hill. Flowers was an expert in electronics, particularly telephone switching systems which used valves or vacuum tubes. He was maybe uniquely positioned to tackle the immense reliability issues of using so many vacuum tubes together.
You're talking.
The Mark V Colossus, the first one, used about 1,500 vacuum tubes. The improved Mark VII version, deployed in 1944, had 2,400. That is just an enormous number of fragile, heat-generating, and frankly, failure-prone components.
Keeping it running must have been a nightmare.
A Herculean task for its dedicated operators, mostly Wren's Women's Royal Naval Service personnel. Constant maintenance, constant vigilance. And its features were astonishing for the era. It processed data from a punched paper tape loop input at an incredible 30 miles per hour.
30 miles per hour for paper tape.
Yeah, translating to about 5,000 characters per second. That speed was essential for trying out different decryption keys quickly. Programming it was done manually, using switches and patch cables like an old telephone switchboard.
So setting up each new code-breaking task took ages.
Oh yeah, incredibly laborious and time-consuming. And crucially, as you hinted earlier, it was not a general-purpose computer. It was purpose-built for a very specific task: pattern matching and counting statistics for cryptanalysis.
So it excelled at that one job.
Brilliantly. but it couldn't be repurposed for, say, calculating artillery tables without a complete redesign. Yet its speed, its electronic nature, it laid such a vital groundwork for what came next.
And what came next, moving across the Atlantic, was the ENIAC, or Electronic Numerical Integrator and Computer. This one had an immediate and profound impact on global history, didn't it?
Absolutely. Its very first operational use, even before it was fully finished, was evaluating the feasibility calculations for the hydrogen bomb. Talk about high stakes.
Right from the start.
This machine was built at the University of Pennsylvania's Moore School of Electrical Engineering, primarily for the Army's Ballistics Research Laboratory, the BRL we mentioned. The initial motivating application was actually calculating artillery firing tables.
Sounds less dramatic, but still vital.
Oh, incredibly vital for accuracy in wartime,
Yeah.
but also incredibly tedious and error-prone to do by hand with human computers. ENIAC promised to automate that.
So tell us about ENIAC. It was even bigger than Colossus.
Oh, much bigger. ENIAC, designed and built mainly by J. Presper Eckert and John Moshley, was publicly unveiled on February 15, 1946. It was a staggering machine by any measure. It boasted an astonishing 17,468 vacuum tubes.
17,000, wow.
Yeah, plus 70,000 resistors, 10,000 capacitors. It consumed a colossal 174 kilowatts of power, enough to apparently dim the lights in parts of Philadelphia when it cycled on.
Incredible. And the size.
Immense. About 80 feet long, 8 feet high, 3 feet deep, and weighed 30 tons. Reliability, again, was a constant concern because of all those vacuum tubes. They failed frequently, especially during power up or down.
So they kept it running.
Often, yes. To mitigate that thermal stress, it was frequently left on continuously for weeks or even months at a time. And like Colossus, programming was achieved through this complex maze of setting switches and plinking patch cables between units. Reconfiguring it for a different problem was a monumental task, often taking days.
And also not general purpose.
Correct. Similar to Colossus, it wasn't a general-purpose computer in the modern sense. It was essentially a giant, incredibly fast electronic calculator, undemised for specific numerical operations, mainly solving systems of differential equations. But these early machines, even though limited in scope, undeniably laid the conceptual and engineering groundwork. They demonstrated the immense power and potential of electronic computation and paved the way for the stored program concept, which was developed around the same time and which truly defined general-purpose computing.
They really weren't just technical marvels. They were so intricately intertwined with these pivotal moments in human history, code-breaking, the dawn of the nuclear age. It's also worth briefly acknowledging some other early pioneers, right?
Absolutely. We should mention Konrad Zeuss's Z3 from 1941 in Germany. Many consider it the world's first working, programmable, fully automatic digital computer. It used electromechanical relays, not electronics, but crucially used binary floating point numbers. A remarkable achievement under difficult circumstances.
And in the UK.
The Manchester Mark I, developed at the University of Manchester, led to the Ferranti Mark I in 1951. This was one of the first commercially available general-purpose electronic computers. And it was a vital, practical implementation of the stored program concept, the idea you could store the program instructions in the computer's memory, just like Beta, rather than having to rewire the machine for each new task. That was revolutionary.
So Colossus and ENIAC showed the power of electronics, Zeus showed programmability, and Manchester Ferranti brought in the stored program. Vital steps on the journey.
Exactly. Each played a crucial role.
Okay, now as we move into the 1950s and 60s, the pace of progress just really starts to accelerate. It feels exponential almost. This era saw incredible advancements in computer technology.
It really took off.
And initially, what we probably call mainframe supercomputers, they serve both business and scientific applications, right? Kind of doing double duty.
Yeah, in the early days, the lines were a bit blurrier. The most powerful machines handled whatever complex tasks were thrown at them, business or science. But here's where it gets really interesting, as you said. There was a clear and, I think, decisive shift over time. Supercomputers started becoming much more science-oriented.
Why that shift?
Well, the complex, data-intensive, and just sheer computationally demanding requirements of scientific research, think simulating nuclear reactions, fluid dynamics, weather modeling, cryptographic analysis, they rapidly outstrip the needs of typical business data processing.
Like payroll or inventory.
Exactly. Those tasks, while important, eventually could be handled by increasingly powerful but less exotic commercial mainframes. The absolute cutting edge, the supercomputers, became specialized tools for science and engineering.
And this era was defined by some groundbreaking new technologies that really pushed the boundaries.
Oh, absolutely. These were game changers. Magnetic core memory, for instance. It replaced slower, less reliable memory technologies like mercury delay lines or Williams tubes. Core memory offered much faster access and was non-volatile, meaning it kept its data even when the power was off. Huge improvement.
In no more vacuum tubes.
The transistor. Transistor logic circuits were revolutionary. Replacing those hot, bulky, unreliable vacuum tubes with tiny, cool, reliable transistors vastly improved reliability, dramatically reduced physical size, and drastically lowered power consumption. It made much larger, more complex machines feasible.
Well,
Floating point hardware became standard. Instead of doing calculations on integers or simulating floating point in software, which was slow, dedicated hardware units could perform the precise high-accuracy calculations with decimal points that are absolutely essential for scientific and engineering work.
speeding up the math.
Massively. And pipelining, which we discussed, overlapping the execution stages of instructions further enhanced speed. And critically, the advent of high-level programming languages like Fortran, formula translation, specifically designed for scientific and engineering computation.
It made them usable by scientists, not just wizards.
Exactly. Fortran and later others like AlGOL and COBOL for business, along with the sophisticated compilers needed to translate that human-readable code into machine instructions, made these powerful machines actually programmable by a wider range of scientists and engineers. You didn't have to be a machine language specialist anymore. It democratized access to this immense power.
You can really see the foundational pillars for modern computing being laid right here, driven by these new technologies. Let's look at some of these pioneering mainframe examples. First, the UNIVAC LIRC Livermore Advanced Research Computer.
Right, LIRC.
Begun in 1955 for Livermore National Lab, delivered in 1960, it actually had dual processors. That seems way ahead of its time for 1955.
It really was. LIRC was a trailblazer in that respect, definitely foreshadowing the multi-processor architectures that would become standard much later. It also used decimal arithmetic, which is a bit unusual for a scientific machine, but may be useful for certain precision tasks, and employed cutting-edge tech for its time, surface barrier transistors, and core memory. Only two were ever built, one for Livermore and one for the Navy's David Taylor Model Basin, a massive, ambitious machine.
And IBM wasn't sitting still either. They had this 7030 known as Stretch.
Ah, yes, Stretch, delivered to Los Alamos in 1961. This machine was hugely influential within IBM. It pioneered many architectural concepts and implementation techniques, really pushing the limits of transistor technology and high-speed memory design for IBM. It didn't quite meet its ambitious performance goals, which caused some embarrassment for IBM, but the project was incredibly valuable for their future designs, particularly the System 360.
And then there was Harvest. Sounds intriguing.
Harvest, or the IBM 7950. Delivered to the NSA in 1962. This was even more specialized. Harvest was essentially a stretch machine, the main computer, but augmented with 4 highly specialized hardware boxes.
Specialized how?
There was a stream unit designed for extremely high-speed processing of serial data streams, vital for cryptanalysis, a massive core storage unit for rapid data access, a specialized tape unit system for handling huge volumes of data on magnetic tape, and an I/O exchange to coordinate all this high-speed input and output.
So early modularity and specialization.
Exactly, dedicating entire hardware units to specific tasks to boost overall system performance, tailored specifically for the NSA's intelligence applications like code breaking, which demanded incredible data throughput, a very sophisticated design for its time.
But then a true legend enters the scene. Seymour Cray. He and Bill Norris famously left UNIVAC to start Controlled Data Corporation CDC, with a very clear vision, right?
Absolutely. Cray was focused. His CDC 1604, launched around 1960, was one of the first truly successful commercial transistor-based computer systems. But his real ambition was clear: to build the undisputed scientific supercomputer.
And that vision materialized with the CDC 6600?
The 6600, shipped in September 1964. Built with faster silicon transistors, not the earlier germanium ones, Seymour Cray and Jim Thornton were the chief architects. This machine just redefined high-performance computing.
What made it so special?
Cray's design philosophy was radical. He built it with a remarkably simple instruction set shades of RISC decades early. He deliberately left out complex instructions like decimal arithmetic because they slowed things down. Speed was everything.
And the parallelism.
That was the real key. It featured 10 independent arithmetic function units, things like adders, multipliers, dividers, shifters, all able to operate simultaneously in parallel. This overlapped execution style, where multiple instructions are processed concurrently using different units, is what we now call superscalar execution.
How did it manage that? Keep track of everything.
With a very clever piece of hardware circuitry that became famous, the scoreboard. The scoreboard tracked which functional units were busy, what data they needed, and where their results were going. It allowed the processor to issue new instructions to available units, even if earlier instructions hadn't fully completed, maximizing parallelism while ensuring data dependencies were respected. Ingenious.
Wow. Anything else notable?
Yes. It also introduced the novel idea of using separate, simpler processors just for handling input-output. And these I/O processors used multi-threading, allowing multiple independent instruction streams to execute concurrently within these simpler I/O units, preventing I/O from becoming a bottleneck for the powerful central processor. A brand new idea then.
So that anecdote fits. Some say RISC means really invented by Seymour Cray.
It really captures the foresight of his design philosophy, focusing on simplicity, speed, and parallelism. And just to top it off, it came with this incredibly futuristic operator's console with multiple CRT displays. Provided at no extra charge, it was both highly functional and a clear statement of technological prowess.
Now, speaking of IBM, Tom Watson Jr., their legendary CEO, was famously not happy about the 6600.
Not happy is an understatement. He apparently wrote a scathing internal memo when the 6600 came out.
Right, the quote is amazing. Last week, Control Data announced the 6600 system. I understand that in the laboratory developing the system, there were only 34 people, including the janitor. Of these, 14 are engineers and 4 are programmers. Contrasting this modest effort with our vast development activities, I fail to understand why we have lost our industry leadership position by letting someone else offer the world's most powerful computer.
Ouch. That really highlights the shockwaves the 6600 sent through the industry and the intense competitive pressure. IBM had to respond.
And their answer was the System 360 Model 91, sometimes called the 370195 later, delivered to NASA Goddard in October 1967.
The 36091 was IBM's counterpunch, a very powerful machine, implementing advanced techniques like multiple execution units and out-of-order execution, trying to match or beat the 6600's performance while staying compatible with their successful System 360 architecture.
And here's a killer application that shows the real-world impact these mainframes had, even beyond pure science: the passenger airline reservation systems. Sabre, for American Airlines, was a huge IBM project.
Yes, Sabre Semi-Automated Business Research Environment was a landmark system, jointly developed by IBM and American Airlines, launched in the early 60s, originally written entirely in complex IBM assembly language. It revolutionized the airline industry, allowing real-time booking and inventory management on a massive scale. It was one of the first huge online transaction processing systems.
Still the foundation of how we book flights today, really. The 36091, performance-wise, how did it stack up?
Very close to the next CDC machine, the 7600. The 36091 was a complex, powerful machine, and like the 6600, it also featured an impressive, very large operator's console. Competition was fierce.
So Cray didn't rest on his laurels. Next came the CDC 7600.
It's the 7600, yeah. An evolution of the 6600 design delivered to Livermore in early 1969. It was designed to be highly compatible with the 6600 software-wise, which made upgrading easier for labs that already had 6600s, but it pushed performance much further.
What was the key advancement?
A key advancement was that its arithmetic units were all deeply pipelined. Remember our assembly line analogy. This meant the units were almost never idle. As soon as one calculation finished its first stage and moved to the next, another calculation could begin its first stage. This ensured continuous operation and maximized the throughput of calculations.
Faster pipeline. And it had cooling issues.
Yes. Its design was incredibly compact for its power, densely packed with integrated circuits. It generated so much heat that it required freon cooling. Refrigeration, essentially. This was an early telling sign of the significant thermal challenges that would become a major headache in high-performance computing, as components got smaller, faster, and packed closer together.
Still, quite a machine.
Oh, absolutely. Seymour Cray himself reportedly considered it one of the world's most beautiful computers, a testament perhaps to its elegant engineering and functional design. It truly cemented CDC's position under Cray's leadership at the very top of the supercomputing world for that period.
It's just incredible to see how quickly performance jumped in this era, the 60s, and how the focus really sharpened onto specialized scientific and defense tasks. And even the consoles, these massive control centers, they were becoming works of art in themselves, reflecting the pride and ambition behind these groundbreaking machines.
It was a golden age of innovation, driven by fierce competition and critical national needs.
Okay, so as we entered the late 1960s and early 70s, it became really clear that even these incredibly powerful mainframes, the 6600, the 7600, the 36091, they just weren't going to be enough for the next wave of problems.
The demands kept growing.
Exactly. The sheer scale and complexity of scientific modeling, defense simulations, code breaking, it demanded even greater performance. And this led directly to a major architectural shift, the development of SIMD array machines. Back to SIMD, but on a much grander scale.
Yeah, this is a really pivotal moment. Designers were hitting walls. How do you make a computer dramatically faster when you're already pushing the inherent physical limits of single processor speed and miniaturization?
Can't just make the clock tick faster forever.
Right. The answer wasn't simply to build bigger, faster single processors indefinitely. The physical limits, clock speed, heat dissipation, even the speed of light for signal propagation delays within a chip were becoming apparent. SIMD array systems were a critical step in a new direction. The idea was essentially to create a machine with many arithmetic processing units that could all execute the same instruction on different pieces of data simultaneously.
A synchronized swimming team, but massive.
Exactly. A way to achieve massive parallelism, but specifically for problems that fit that SIMD model, the same operation repeated over huge data sets.
One of the earliest and maybe most ambitious of these was the ENIAC IV, a joint project between the University of Illinois and the Burroughs Corporation.
Ah, ENIAC IV, a famous, perhaps infamous machine.
Funded by DARPA starting way back in 1964, but it wasn't really fully usable until 1975. That's a very long development cycle.
11 years. Tells you how hard it was.
The chief architect, Dan Slotnick, had this incredibly ambitious plan originally for 256 separate arithmetic units or processing elements. That got cut back to 64 in the final machine, mainly due to engineering difficulties and spiraling costs.
Still, 64 processors working in lockstep was revolutionary then.
Absolutely. But they had major headaches, didn't they? Particularly with the memory.
Yes, the memory system was a nightmare. They were trying to use a new technology called thin film magnetic memory, which promised high speed but proved incredibly difficult to manufacture reliably at the scale needed. It caused huge delays and problems.
And then there was the move.
Yes. The political dimension. In May 1970, there were significant student demonstrations and protests at the University of Illinois against military-funded research on campus, this being the height of the Vietnam War era. As a direct result, the entire ENIAC V project, hardware and all, was literally moved from Illinois to the NASA Ames Research Center in California.
Wow. Just packed it up and moved it. Really highlights the human and political factors that can swirl around even these highly technical bleeding-edge projects.
Absolutely. But despite the challenges, ENIAC V spurred significant advancements, especially in software. Languages like IVTran and CFD were created specifically to help programmers express and utilize the machine's inherent parallelism. A lot of compiler expertise for parallel programming was developed trying to tame that beast.
And ENIAC V led to other designs.
Yes, Burroughs leveraged the experience. They developed PEPE, the Parallel Element Processing Ensemble. Delivered to the Ballistic Missile Defense Advanced Technology Center, BMD-ATC, in Huntsville in 1976. PEPE was a massive machine with 288 specialized processing elements, purpose-built to track incoming ballistic missiles and process radar data in real time. Very specialized defense application.
And the BSP.
The BSP, or Burroughs Scientific Processor, was another descendant. This one with 16 more powerful processing elements aimed for the commercial scientific market, things like oil exploration, seismic data processing. Marathon Oil was lined up as the first customer. But unfortunately, the BSP project was canceled in 1980 before its first delivery.
Why?
Probably a combination of factors. The immense challenge and risk of commercializing such cutting-edge specialized technology, finding a broad enough market niche, managing the costs. It's just proved too difficult, illustrating the high failure rate in this demanding field.
Okay, following that path, we saw the emergence of something slightly different, one-bit arrays.
Right, the one-bit wide processors.
As the name suggests, these were arrays of processors that were, well, only 1 bit wide computationally. This made them incredibly inexpensive to implement, especially as chip manufacturing technology improved, allowing many on a single chip.
Cheaper building blocks.
Exactly. And what's neat, the lecture notes point out, is that their arithmetic was done serially, bit by bit, kind of like how we learned binary addition in grade school. This meant they could handle variable precision arithmetic easily. You just kept processing more bits if you needed more accuracy. Very flexible for certain tasks, particularly bit-level operations or associative processing.
And who is behind these?
Ken Batcher, who actually graduated from Illinois and had worked on the ENIAC IV, was the chief architect behind Goodyear Aerospace's STARAM, developed in 1972.
Goodyear, like the tires.
Goodyear Aerospace, yeah, a different division. STARAM was initially conceived as an associative processor, good for searching large databases quickly. It was a 256 by 256 array with immense data permuting power. But it turned out to be surprisingly excellent at image processing and pattern recognition, even though that wasn't its original main goal.
Found its niche.
Totally. And a militarized version called ASPRO for associative processor was even used on Navy E-2C Hawkeye AWACS aircraft for real-time signal processing and target tracking. High-impact, real-world use.
Wow, on an airplane.
Then Goodyear followed up with the MPP, the massively parallel processor, in 1984. This was essentially a single-chip successor to STARAM, integrating the processing elements much more densely. Its array size was 128 by 128, but with significantly increased speed. It was delivered to NASA Goddard, where it was a workhorse for processing satellite imagery and running climate models for years.
So NASA was a big user of these arrays.
Definitely. And the UK wasn't idle either. ICL, International Computers Limited, developed its own distributed array processor, or DAP, architected by Stuart Redaway, exploring a similar one-bit array paradigm, often attached to a mainframe host.
Interesting. And then came a really famous one, the connection machine.
The CM series. Iconic. It originally grew out of Danny Hillis's PhD thesis at MIT. His idea was based on a connectionist approach to artificial intelligence, the theory that intelligence emerges from the interactions of many simple processing units connected in a dense network, kind of like neurons in the brain.
AI-inspired hardware.
Exactly. The first machine, the CM1, was a hypercube-connected array of thousands of these simple one-bit processors, designed to efficiently process highly interconnected data, like semantic networks and AI. Crucially, it offered excellent high-level language support, which made it much easier to program than some predecessors, and it proved surprisingly useful not just for AI research, but also for general scientific computation involving large datasets.
And the CM2.
The successors, the CM2, and later the CM200, made a critical addition. They added standard 32-bit floating-point hardware alongside the bit serial processors. This was absolutely essential for the scientific and engineering applications that demand high numerical precision.
Made it attractive to the big labs.
Totally. It made them highly attractive to the big high-performance computing users like the NSA and Los Alamos, who bought several of them. I always loved the visual of the CM2, that big black cube with the array of blinking red lights on its surface.
Blinking lights.
Exactly. They pulsed with the computation.
Yeah.
Okay, sadly, there wasn't one light per processor. That was apparently too expensive, but it looked incredibly cool and futuristic. A real visual icon of parallel computing.
It's also important to note, as the lecture points out, that the later CM5 was a significant evolution. It actually shifted away from the SIMD one-bit array model to a MIMD architecture using standard microprocessors. Shows how these designs continuously adapted based on technology and user needs.
Good point. Now, following a slightly different SIMD path, another powerful approach emerged around the same time. Vector pipelining?
The vector machine.
Specifically designed, as the lecture says, to exploit the repetitive nature of Fortran loops, which are incredibly common in scientific code. DOI equals 1 to n, AI equals BI plus CI.
Right.
That kind of thing.
Perfect for vector operations.
The Texas Instruments Advanced Scientific Computer, or TIASC, in 1974, was an early and influential example here. Its Fortran compiler was apparently considered state-of-the-art for its ability to automatically analyze code, find those loops, and generate efficient vector instructions for the hardware. A significant software engineering achievement.
Where did they end up?
Several systems were shipped to crucial scientific institutions. The Geophysical Fluid Dynamics Laboratory, GFDL, at Princeton for climate modeling, Ballistic Missile Defense in Huntsville, the Naval Research Laboratory. They were used for large-scale simulations. And there was a quirky detail about the GFDL machine.
Yeah, the lecture mentions this, almost a piece of historical whimsy. The GFDL machine apparently had a strip chart recorder, like you'd see in a lab, perched right on top of the console, and it would plot the length of the vectors being processed during your program's execution. You got the paper chart back with your printout.
A literal graph of your vectorization.
Exactly. A tangible visualization of how efficiently your program was using the machine's special vector capabilities. Amazing.
Yeah. Okay, then there was CDC's entry into vectors, the star 100.
Right, the star 100. CDC took a slightly different approach here. Instead of focusing solely on Fortran DO loops, they used the concepts from APL, a programming language, a very powerful, concise, array-oriented language invented by Ken Iverson at IBM Research as their conceptual model for vector operations. Neil Lincoln and Jim Thornton were the architects again, with Sidney Fernbach at Livermore being the initial target customer.
But the star 100 had a problem.
A major flaw, unfortunately. While its peak vector performance for specific, highly parallelizable tasks could be excellent, its scalar performance, that is, the speed for the parts of the program that couldn't be vectorized was quite poor.
Uh-oh. Sounds like a recipe for trouble.
Exactly. This is precisely where Amdahl's law comes roaring back into the picture. It's a concept that has just echoed through supercomputing design ever since, serving as a stark warning.
Remind us of Amdahl's law again.
Gene Amdahl, who was a key architect at IBM on the System 360, articulated it. Basically, it says that the maximum speedup you can get by parallelizing part of a program is limited by the fraction of the program that must remain sequential.
The non-parallel part holds you back.
Precisely. The formula is, if a fraction of work W1 is done at a sped-up rate S1, but the remaining fraction W2 can only be done at the original speed S2, then the overall average speed S is W1 plus W2, W1 S1 plus W2 S2.
Let's use the example from the lecture.
Okay, imagine 90% of your program's execution time, W1 units of work, can be sped up by a factor of 100, S1 100, using vectors. Sounds amazing, right? Huge speed up.
But the remaining 10% of your program, W21 unit of work, is inherently sequential and can only be done at the original speed, S21. Your overall speedup isn't 90x or even 10x. It's actually 9 plus 1, 9100 plus 11.
It is
10.09 plus 1. That's only about a 9.17x speedup. That tiny 10% sequential part drastically limits the overall benefit of your 100x vector speedup.
Wow, Amdahl's law bites hard.
It really does. And for the star 100, its poor scalar performance meant that Amdahl's law hit it hard. It had highly limited applicability, only really useful for problems that were almost entirely vectorizable. Los Alamos National Lab, seeing this limitation, actually backed out of their order.
They canceled.
Yeah, they switched their order to the upcoming Cray 1 instead. Livermore, however, ended up getting both of the star 100 systems that were built. It really highlights the very real-world consequences and trade-offs of architectural choices and how Amdahl's law can make or break a supercomputer design if you don't balance scalar and vector performance.
Okay, and that brings us perfectly to the icon itself.
The Cray 1.
At the Cray.
This machine truly stands apart. And Seymour Cray's approach was different from the start, wasn't it? No government contract.
That's right. Unlike the Star 100 or ENIAC the Fifth, Seymour Cray actually refused a government development contract for the Cray 1. He famously disliked governments looking over his shoulder, preferring to work independently with his own team in Chippewa Falls, Wisconsin, free from bureaucratic oversight. A maverick approach.
And he made a bold move to sell the first one.
Incredibly bold. Cray Research finished the first Cray 1 in 1975. They offered Los Alamos National Laboratory a 1-year free trial. Just install it, use it, see if you like it.
Wow. Talk about confidence in your product.
Absolutely. And Cray provided almost no software with it. Los Alamos engineers had to develop or adapt existing operating systems, compilers, and libraries for this completely new architecture. It was a huge undertaking for them.
Did they keep it?
They did. After the year, Los Alamos was thoroughly convinced of its power and signed a lease. And interestingly, the lecture notes mention the financing was apparently provided by a New Mexico petroleum magnate, showing the sometimes unusual pathways for funding this kind of cutting-edge tech.
So what made the Cray 1 so successful, especially after the Star 100's issues?
It succeeded precisely because it definitely did not suffer from Amdahl's law nearly as badly. Seymour Cray understood the pitfalls of unbalanced designs. The Cray 1's scalar performance alone, for the non-vector parts of code, was roughly twice that of the already powerful CDC 7600. That was huge.
So the sequential bits ran fast too.
Exactly. And then, once the vector software matured, allowing applications to effectively utilize its powerful pipeline vector processing units, the overall performance gains became 8 times or more compared to the 7600 on suitable codes. This crucial balance of excellent scalar performance and superb vector performance made it incredibly versatile and powerful for a wide range of scientific problems.
The best of both worlds, balanced.
Pretty much. It was so impactful, so distinctive with its iconic C-shaped design to minimize wire links, and its colorful padded bench surrounding the base. that even today, when people say supercomputer, they often still picture the Cray 1. It cemented Seymour Cray's legacy as the unparalleled master of supercomputer design and set a new standard for high-performance computing for over a decade.
A true icon. Now, finally, in this SIMD-vector era, we also saw the emergence of VLIW systems, very long instruction word.
Right, VLIW.
The lecture describes these as a kind of SIMD, where each arithmetic unit can actually be doing something different simultaneously, all controlled by fields within a single, very long instruction word, hence the width needed for the instruction.
Yeah, a different way to achieve instruction-level parallelism. Instead of hardware finding parallelism dynamically, like superscalar, the compiler finds it statically and packs independent operations into one big instruction.
And the lecture notes mention these weren't technically supercomputers by the strict fastest at the time definition, but they were significant.
Exactly. They occupied an important niche, often as specialized array processors or accelerators. Floating point systems, or FPS, was a pioneer here, starting in 1976 with their AP120B architected by Glenn Culler. These were essentially powerful co-processors designed to accelerate floating point math.
Where were they used?
They found real practical applications. Many were embedded inside GE PAT scanners, performing the complex mathematical image reconstructions needed for medical imaging. They were also widely used in the oil and gas industry for seismic data processing, sifting through huge amounts of geological data, showed the value of specialized parallel processors for specific domains.
And later VLIW companies.
In the mid-80s, there was a resurgence. Multiflow was founded in 1984 by Josh Fisher, specifically to commercialize groundbreaking VLIW compiler technology he had developed at Yale. Their Trace 7200 machine shipped in 1987, aiming to extract massive amounts of instruction-level parallelism automatically. Around the same time, Bob Rao's company, Sidrome, also founded in 1984, demonstrated their Sidra 5 machine in 1987.
How complex were their instructions?
Both the Trace and the Sidra 5 had incredibly wide instructions, maybe 7 independent operation fields packed into 256 bits, trying to schedule many different functional units in parallel with every single instruction. Very ambitious compiler technology was needed.
But they weren't top-tier supercomputers.
Technically, no, not the absolute fastest general-purpose machines, but they were part of this broader trend towards specialized parallel processing. And this is where we can also maybe mention digital signal processors, or DSPs.
Right, the lecture notes bring those in here.
DSPs emerged as kind of low-cost, highly specialized supercomputers optimized for specific tasks like processing audio signals, video, radar signals. They often use VLIW-like architectures internally, tuned for those kind of continuous data stream calculations.
And the Sellic arrays.
Systolic arrays were another fascinating parallel architecture explored around this time. Imagine a network of simple processing units where data flows rhythmically through them, getting processed at each step, kind of like blood pulsing through arteries, hence systolic. They were particularly good for highly structured computations, like matrix multiplication or image filtering.
And these specialized approaches led somewhere important.
Yes. These specialized parallel architectures, VLIW, DSPs, systolic arrays, they can absolutely be regarded as direct conceptual predecessors to the powerful graphics processing units, or GPUs, that we rely on so heavily today.
Ah, the GPU connection.
Exactly. GPUs took these ideas of massive parallelism, often SIMD-like execution on many simple cores, initially for graphics, but then generalized them. GPU, general-purpose GPU computing. GPUs have become absolutely critical components not just in modern supercomputers for accelerating scientific simulations, but also as the engines driving the incredible recent progress in artificial intelligence and deep learning. Their lineage traces back to these earlier explorations in parallel architectures.
Wow. So we're really seeing this clear shift, aren't we? Moving away from just building bigger, faster single brains towards building many smaller, often specialized brains working together in concert. And we've also absorbed that critical, sometimes painful lesson of Amdahl's law, that the sequential parts of a program can truly be the Achilles heel for overall speed-up, no matter how much parallel power you throw at the rest of it. Balancing the design is key.
Absolutely. That balance and the challenge of programming these parallel ensembles effectively became the central themes moving into the next era.
Our journey continues now, and we're hitting a really fundamental and frankly massive shift. The move towards MIMD architectures really starts to dominate the supercomputing landscape from the 80s onwards. This marks a significant evolution in how these powerful machines are designed and used.
Yeah, this is a major turning point. What's truly fascinating here is how designers really started to tackle the inherent limits of those single instruction streams, the SIMD model, by giving multiple processors their own independent instructions.
Multiple instruction stream, multiple data stream, MIMD.
Exactly. This enabled true asynchronous parallel processing. Processors could be working on completely different parts of the code at the same time. It was a critical architectural divergence from SIMD's lockstep approach. We moved from that one instruction to many data model to a many instructions to many data model,
Unlocking more power.
unlocking unprecedented levels of computational power, yes, but also tackling a broader and more diverse range of complex problems that didn't fit the rigid SIMD mold. This shift was largely driven by the increasing difficulty and, frankly, the prohibitive cost of continually pushing single processor clock speeds much higher. Plus, there was this growing recognition that scaling performance effectively had to come from adding more independent computational units, capable of tackling different parts of a complex problem simultaneously.
More brains working independently.
That was the path forward. And within IMD, we first saw developments in shared memory systems continue, building on earlier ideas but scaling them up. Seymour Cray's own vector systems continued this line. The Cray 1 was single processor, but then came the Cray 2 in 1985.
How many processors did that have?
It typically had up to 4 processors sharing a very fast, very large common memory. There was even one special 8-processor Cray 2 built, really pushing the boundaries of shared memory scaling at the time. It was famous for its immersion cooling. The whole thing was submerged in floor-inert liquid to keep it cool.
Wow. And Cray Research, the company after Seymour left.
They continued down the shared memory vector path for a long time. There was the Cray XMP with up to 4 processors, then the hugely successful YMP with up to 8, the C90 scaling to 16, and the T90 reaching up to 32 processors in the mid-90s, all powerful vector machines sharing memory.
Still vector processing, but multiple processors sharing memory.
Right, combining vector speed with MIMD parallelism. Their Cray X1, much later in 2003, was a massive leap, designed to support up to potentially 800/192 processors. And significantly, the X1 was one of the first massively parallel systems from Cray that embraced a UMA architecture, that non-uniform memory access, acknowledging the scaling limits of true UMA, a big shift for them.
And Seymour Cray himself, after leaving Cray Research.
He started Cray Computer Corporation and continued chasing speed with exotic technology. His Cray 3, using gallium arsenide chips instead of silicon for higher speed, aimed for up to 16 processors. And the follow-on Cray 4 was targeting up to 64 processors before the company unfortunately went bankrupt in 1995. He was always pushing the absolute limits.
Now, another important development in shared memory MIMD was multi-threading. What's the idea there?
Multi-threading is a technique to essentially pipeline the MIMD architecture, kind of analogous to how vector systems pipeline SIMD. The idea is to have multiple instruction streams or threads ready to execute within a single processor.
Why do that?
To keep the processor's various functional units busy. If one thread has to pause, perhaps waiting for data to arrive from memory, a common bottleneck, especially in shared memory systems, the processor can instantly switch to executing instructions from another ready thread. It hides the latency and maximizes utilization.
Keeping the pipeline full, but with different threads.
Exactly. Multi-threaded systems could be built using either UMA or NUMA memory models. Some key pioneering examples include the Denel Core HEP from way back in 1980, one of the first general-purpose multi-threaded machines. Then later, the Terra MTA1 in 1998, and its successor, the Cray MTA2 in 2002, which Cray acquired. These machines could handle hundreds of threads per processor and scaled up to 256 processors. Very influential designs for certain types of irregular computations.
And this relates to something in desktop PCs.
Yes. A common variant you might have encountered is simultaneous multithreading, or SMT. Intel famously brands this as hyperthreading in their desktop and server processors. SMT allows a single physical processor core to execute instructions from multiple threads concurrently by dynamically sharing the execution resources between them. It makes one core look like 2 or more logical cores to the operating system, again boosting throughput.
Okay. Then we have cache-coherent NUMA, or CC NUMA systems. You mentioned NUMA earlier. What does the cache-coherent part add?
Right. CC/NUMA became a really important approach for building large-scale shared memory systems. It was heavily researched at universities like Stanford in the late 80s and early 90s, and companies like Silicon Graphics, SGI, turned that research into highly successful commercial products. Kendall Square Research, KSR, also pursued a related variant they called COMA for cache-only memory architecture.
So how does CC-NUMA work?
These systems represented a much more sophisticated evolution in memory management for NUMA. The cache-coherent aspect is absolutely critical. It means the hardware automatically manages the movement of data between the private caches of all the different processors across the distributed memory nodes.
Keeping the caches consistent.
Exactly. It ensures that if one processor modifies a piece of data, all other processors' cached copies are either updated or invalidated, so everyone always sees a consistent, correct view of memory. Crucially, if a processor needs data that happens to be currently sitting in another processor's cache, the hardware automatically fetches it across the network.
Making NUMA easier to program.
Significantly easier. This cache coherence mechanism automatically handles most of the complexity of data placement and synchronization, largely offloading that burden from the programmer back onto the hardware. It made UMA systems feel much more like programming a simpler UMA system while still allowing them to scale.
And SGI was big in this space.
Hugely successful. SGI's CC UMA systems like the Origin 2000, the Origin 3000, and later the Altix series scaled up to hundreds, Altix up to 512 of processors, and became workhorses in scientific computing, engineering simulation, and high-end data visualization. Kendall Square's COMA systems, the KSR1 and KSR2, went even further with their cache-only approach, treating main memory itself as just another level of cache, aiming for thousands of processors. The KSR2 supported up to 5,000 processors, really showcasing the ambition for massive scaling within a model that still looked like shared memory to the programmer by aggressively using caches as the primary memory abstraction.
Fascinating stuff. But you said earlier the architecture that really dominates supercomputing today is distributed memory, MIMD.
Yes. Here's where things get, well, dominant for the largest systems. In these, remember, the memory is explicitly partitioned. Each processor has its own private address space, its own notebook, and they communicate only by explicitly sending messages to each other. This is the fundamental shift that truly unlocked unprecedented scalability.
And this model really took off with a project at Caltech.
The Cosmic Cube, absolutely seminal work, pioneered by Chuck Seitz and Jeffrey Fox at Caltech around 1982. This groundbreaking system featured 64 standard Intel 8086 microprocessors, each paired with an Intel 8087 floating-point coprocessor for math speed.
How were they connected?
In a six-dimensional hypercube topology, this network structure was critical. It offered excellent connectivity for 64 nodes. Each processor was directly connected to 6 neighbors, and the maximum number of hops or messages needed to get data between any 2 processors in the system was only 6. This provided efficient communication paths, minimizing latency.
And they used message passing.
Explicitly. Processors communicated only by sending messages. This paradigm, demonstrated so effectively by the Cosmic Cube, proved incredibly scalable and, as you said, now forms the backbone of virtually all modern large-scale supercomputing. Early commercial systems quickly followed, inspired by the Cosmic Cube, like the Amitex 14, the Intel IPSC-1, Intel Personal Supercomputer, and the NCU BE-10, which scaled impressively up to N124 processors very early on, showing the rapid industry adoption of this scalable message passing architecture.
And the variations since then led to what we call classic MPPs.
Right, massively parallel processors, or MPPs, where the individual processing elements, the nodes, are typically full-fledged microprocessors, often the same kind you'd find in servers or workstations. We've seen just a parade of titans in this space. Cray eventually jumped in big time with their T3D, T3E, and later the XT series, highly successful distributed memory machines. Intel had their Touchstone series, Delta, Gamma, Paragon. IBM had their SP series, SP1, SP2.
And Deep Blue.
And Deep Blue, absolutely. IBM's ST2-based machine that famously beat world chess champion Garry Kasparov in 1997, that really captured the public imagination, didn't it? Showed the immense power of these MPPs for tackling complex problems, even ones thought to require human intuition. And IBM later developed the incredibly influential Blue Gene series, pushing density and power efficiency for MPPs.
So MPPs used custom or high-end nodes. What about clusters?
Clusters became another hugely important trend, really democratizing high-performance computing. In a cluster, the processing elements, the nodes, are not necessarily individual microprocessors, but often complete shared memory multiprocessor systems themselves, standard servers, essentially networked together using high-speed interconnects.
So clusters of servers.
Pretty much. Examples from vendors include systems like IBM's eServer P575 clusters, or NEC systems like the SX8, which could be clustered, and of course NEC's Earth simulator from 2002, which I mentioned earlier. While internally it used vector processors, it was a massive cluster architecture. A colossal machine built in Japan, it was the world's fastest for a while, and a global leader in climate modeling, achieving incredible simulation fidelity and showcasing the critical role these large clusters play in scientific discovery.
And the homemade clusters.
Ah, the Beowulf clusters. This was a massive grassroots movement starting in the mid-90s. The idea, pioneered at NASA, was to build powerful parallel computers simply by networking together lots of inexpensive commodity off-the-shelf PCs or servers, typically running the free Linux operating system and using standard Ethernet or other networks.
DIY supercomputing.
Exactly. Suddenly, university departments, research labs, even small companies could build their own supercomputer relatively cheaply. Government labs also built huge Beowulf clusters using standard Intel or AMD processors. This Beowulf revolution demonstrated how the distributed memory message passing model could be scaled both up to massive machines and down to affordable departmental clusters, leading to a real proliferation of computational power.
So we've truly moved, haven't we? From single, immensely powerful monolithic machines to these vast distributed networks of powerful machines, whether they're tightly integrated MPPs or looser clusters of commodity hardware. The story of supercomputing, especially at the high end, is increasingly a story of communication and coordination between tens, hundreds, thousands, even millions of processing units, rather than just raw brute force speed from a single component. It's all about how effectively these many independent brains can work together on a single problem.
That's the essence of modern supercomputing: communication, coordination, and scale.
Now, this intense technological evolution, this race for speed and scale, it wasn't just happening in a vacuum, was it? It really ignited a fierce global race, particularly between Japan and the United States. Supercomputing became a matter of national pride, strategic importance.
Oh, absolutely. It went way beyond just building faster computers. It was seen as critical for economic competitiveness, scientific leadership, and national security. The competitive landscape, especially from the 80s onwards, became incredibly intense.
How did Japan approach it?
Japanese supercomputer companies, primarily the big three Fujitsu, NEC, and Hitachi, largely favored vector processors for a long time, building on the Cray legacy but pushing it in their own directions. Initially, these were often shared memory systems, but more recently, they also moved strongly into distributed memory vector architectures.
Any specific examples?
Sure. Fujitsu started shipping its first vector system, the Facom VP series, back in the late 70s, early 80s, evolving through powerful systems like the VPP 5000 in the late 90s. Interestingly, as the lecture notes mention, Fujitsu later pivoted and started selling scalar and UMA systems as well, showing architectural flexibility. NEC got a slightly later start in vectors, but quickly became a major force with their SX series, beginning with the SX1 in 1983 and progressing through machines like the SX8 in the mid-2000s.
And the Earth simulator was NEC.
Yes, the Earth simulator, which held the top spot on the top 500 list from 2002 to 2004, was a massive NEC SX system, a triumph of vector processor design and integration built specifically for the Japanese government's climate research agency. Tadashi Watanabe was the chief architect behind many of these impressive NEC SX systems, a real giant in Japanese supercomputing. Hitachi also built powerful vector systems, like their S-series, although they had fewer sales outside Japan compared to Fujitsu and NEC. Their distributed memory SR8000 in 2000 was a notable exception that saw some international adoption.
And this wasn't just individual companies competing, right? The Japanese government played a big role.
A huge role. Japan launched the National Superspeed Computer Project in 1981. This was a major national initiative, investing about $23 billion, maybe around $100 million back then over 9 years, with the explicit goal of leapfrogging the U.S. and producing a world-leading supercomputer. It involved all the major players: Fujitsu, NEC, Hitachi, Mitsubishi, Oki, Toshiba, pooling national resources and coordinating research towards that collective goal.
And then the fifth generation project. That sounded even more ambitious.
It was incredibly ambitious, maybe overly so in hindsight. Launched in 1982, the fifth generation computer systems project was a massive $55 billion, around $200 million, 10-year initiative centered at a dedicated lab called ICOF, Institute for New Generation Computer Technology. This project focused squarely on artificial intelligence.
AI back in the 80s.
Yes. The goal was to develop revolutionary new computer architectures and software based on logic programming, designed specifically for AI tasks like inference, natural language understanding, machine translation, vision, and speech processing. The sheer scale and ambition of this project, aiming for intelligent computers, were unprecedented. And critically, it sent shockwaves through the U.S. tech industry and government.
Prompting a U.S. response.
Absolutely. Fear of falling behind Japan spurred a significant U.S. industrial response, most notably the creation of the Microelectronics and Computer Technology Corporation, or MCC, in Austin, Texas. MCC was a research consortium funded by major American tech companies like CDC, DEC, Honeywell, Motorola, NCR, etc., specifically to conduct long-term, high-risk research in areas like parallel processing, AI, and advanced software, partly as a direct counter to the perceived Japanese challenge, especially the fifth-generation project.
And the U.S. government also responded directly.
Yes. DARPA, the Defense Advanced Research Projects Agency, responded vigorously with its own strategic computing program, which ran from roughly 1983 to 1993. This program was explicitly intended to accelerate the development and application of parallel computing technologies, pushing them out of the labs and into practical systems for military and scientific use.
How do they do that?
DARPA strategically funded several key industrial development projects, deliberately encouraging a diversity of parallel architectures rather than betting on just one. This included funding thinking machines for their SIMD connection machine, Bolt, Beranek and Newman, BBN, for their butterfly shared memory machine with its unique network, Intel for its distributed memory touchstone series, which led to Paragon, Terra Computing for their multi-threaded MTA architecture, and even Cray Research for their first distributed memory machine, the T3D.
Spreading the bets.
Exactly. And crucially, DARPA encouraged other government agencies to actually buy and try these novel systems, creating an early market and providing invaluable real-world feedback. This program effectively steered much of American supercomputing development during that critical decade, fostering innovation across different parallel approaches.
Meanwhile, the Department of Energy, DOE, had its own massive supercomputing initiative, right? The ACI program.
Yes, SEI, the Accelerated Strategic Computing Initiative, later renamed ASC. This program had a truly monumental and politically charged directive. Following the U.S. decision to adhere to the Comprehensive Nuclear Test Ban Treaty, the DOE was explicitly tasked by Congress to use advanced computer simulation to ensure the safety, security, and reliability of the U.S. nuclear weapons stockpile without resorting to underground nuclear testing.
Simulation instead of testing. That sounds incredibly demanding computationally.
Unprecedentedly demanding. Simulating the incredibly complex physics of nuclear detonations from initiation to full yield with absolute fidelity and predictive power required computational capabilities far beyond anything that existed in the mid-90s.
So how did DOE tackle it?
To achieve this incredibly challenging goal, the ASCII program procured a series of increasingly powerful supercomputers, primarily distributed memory MIMD systems from various U.S. manufacturers, deploying them at the three main nuclear weapons labs: Los Alamos, Livermore, and Sandia.
Can you name some of these ASCII machines? They had color-coded names, right?
They did. It started with ASCII Red, built by Intel for Sandia National Laboratories, which became the world's first teraflops machine in 1996-97. Then came ASCII Blue Pacific from IBM at Livermore and ASCII Blue Mountain from SGI at Los Alamos. Then ASCII White from IBM at Livermore around 2000, followed by ASCII Q from Compaq HT at Los Alamos in 2002, then Red Storm from Cray at Sandia in 2004, and Purple from IBM at Livermore in 2006.
Just a relentless progression of power.
Absolutely. These systems weren't just incrementally faster. The performance range across this series, from Red to Purple, spanned about a staggering 100-fold increase in computational power in just over a decade. It showcased the rapid advancements driven by this critical national security mandate and the immense investment behind it. These ASCII machines became foundational for the whole field of science-based stockpile stewardship.
Wow. Now, for those of us who want to keep track of the bleeding edge today, you mentioned www.top500.org. It's a great place for some supercomputer spotting, listing the fastest machines twice a year.
It is indeed a fantastic resource, run by Eric Strohmeyer, Jack Dongara, Horst Simon, and Martin Moyer for many years now. It tracks the evolution of the world's most powerful publicly known systems. But, and this is a crucial caveat the lecture also emphasizes, you have to be very careful about the term fastest when you look at that list.
Why is that? What's the catch?
The speed ranking on the top 500 list is primarily measured by one specific benchmark program called LINPACK, specifically the high-performance LINPACK HPL benchmark.
What does LINPACK measure?
It measures how fast a computer can solve a large, dense system of linear equations using floating-point arithmetic. It's basically a test of raw computational throughput for that specific kind of matrix math, which is very common in many scientific simulations.
So what's the problem?
The problem is that LINPACK, especially HPL, doesn't necessarily stress other critical aspects of a supercomputer's performance. It doesn't really care how well the system's interconnection network performs for more communication-intensive applications, or how well it handles irregular memory access patterns. And shared memory, for example, isn't particularly useful for getting good LINPACK results. The benchmark heavily favors distributed memory paradigms where each processor works intensely on its local portion of the matrix.
So it's a narrow definition of fastest.
It's an excellent indicator of peak floating point performance on a specific type of problem, yes, but it's definitely not the full story of a supercomputer's overall utility or efficiency for all kinds of parallel workloads. Some machines might be fantastic at LINPACK, but struggle with applications dominated by data movement or irregular computations. So while the top 500 list is incredibly valuable for tracking trends and pushing vendors, you just need to take the ranking with that grain of salt.
Good context to keep in mind. Still, it's well worth a look.
Oh, absolutely. It's fascinating to see the current state of the art, who's building the biggest machines, what architectures are dominant, and just to observe the incredible growth in global supercomputing power over time.
So this era really saw supercomputing become a high-stakes game of national pride, strategic necessity, driving massive government and industrial investment in both the U.S. and Japan, leading to these incredible leaps in capability, often for highly specialized critical tasks like nuclear simulation or trying to jumpstart AI research. It was definitely a race with very high stakes indeed.
A technological arms race, in many ways, that profoundly shaped the computing landscape we have today.
So after that incredible journey through time, from vacuum tubes cracking codes to globally connected clusters simulating the universe, what's next? What's next for these computational behemoths, and what are the really key takeaways we should hold on to?
Well, looking forward, the most immediate and maybe profound development we're seeing and living through right now is that parallelism, which was once the exclusive exotic domain of supercomputers, is rapidly becoming mainstream. Absolutely ubiquitous.
You mean multi-core chips?
Exactly. We're seeing Intel, AMD, ARM, everyone putting multiple processors, multiple cores onto a single chip. It's standard now in your desktop, your laptop, even your phone. It might only be a handful of cores now in consumer devices, but this trend is only going to accelerate. Chip designers are continuing to face those physical limits, heat, power, speed of light, and making single cores dramatically faster. Adding more cores is the main way forward for performance scaling.
How does that change the supercomputer playing field?
It changes everything eventually. As multi-core becomes the default, the need for parallel application software, for new parallel programming languages and models, and for much more sophisticated compilers that can actually exploit that parallelism automatically. That need becomes universal, not just confined to the high-performance computing niche.
So everyone needs to think parallel now.
Increasingly, yes. This will inevitably blur the lines between what was once considered super and what is simply standard computing. The underlying parallel architecture of all computers will continue to evolve to match these demands. It's a fundamental shift.
And looking even further out, the lecture mentioned the world as one giant cluster.
That's a fascinating, maybe slightly futuristic vision, but the seeds are there. Think about cloud computing, grid computing. We're already linking computers together globally on an unprecedented scale. The potential exists for harnessing this globally distributed computational power in more coordinated ways, like one vast interconnected computational fabric.
For an exciting field, but also challenging.
Right. Immense challenges. As the lecture notes conclude, if we build such powerful interconnected systems, we must also figure out how to make them safe, secure, reliable, and robust against both malicious actors and catastrophic failures. The societal implications are huge.
Definitely. So reflecting back on our whole journey, what are the key takeaways, the distilled wisdom from this rich history?
Okay, let's try to summarize. First, the original supercomputers back in the 60s and 70s were fundamentally single processor machines, maybe with vector units. Their focus was on achieving the absolute fastest clock speeds possible, pioneering vector processing for loop-heavy scientific codes, and incorporating large amounts of fast physical memory. Speed came from raw horsepower in one place.
Then came the RISC insight.
Right. A pivotal realization for designers was that it was often better, counterintuitively, to make the processor's instruction set simple if you wanted the chip itself to run fast. This gave rise to RISC architectures and a relentless focus on instruction execution efficiency and high clock rates.
And pipelining was crucial.
Absolutely essential. Pipelining, that assembly line approach, allowed designers to efficiently execute instructions, even multiple ones simultaneously in superscalar designs, with minimal overhead per instruction. But as we discussed, this placed enormous pressure on compilers to be clever enough to optimize the code and keep those pipelines constantly full and flowing.
Then the big shift to parallel.
Yes, a critical turning point occurred, perhaps around the time clock speeds hit roughly 100 megahertz or so in the late 80s, early 90s. Designers really started to sense the approaching physical limits for conventional integrated circuit technology and ever-increasing clock speeds, limits imposed by the speed of light, by heat generation, by power consumption.
Couldn't just keep shrinking transistors and turning it off the clock forever.
Exactly. This realization forced a dramatic shift in focus across the industry towards massively parallel architectures. It became clear that simply making a single processor faster and faster wasn't going to deliver the orders of magnitude performance increases needed anymore. Parallelism, using many processors working together, became the only viable path forward for significant future gains.
What about the software side?
On the software side, especially for these parallel systems, Linux quickly emerged in the 90s and became the dominant operating system for high-performance computing. Its flexibility, stability, open-source nature, and commodity hardware support made it ideal. However, parallel application software development significantly lagged behind the hardware innovation for many years. It was just really hard to program these complex machines effectively.
Until standards emerged.
Right. Things finally started getting easier, or at least more standardized, with the development and adoption of industry standards like MPI, the Message Passing Interface for distributed memory communication, and later OpenMP for shared memory parallelism, and things like CUDA and OpenCL for GPU programming. These provided common, portable frameworks that helped unlock the power of these parallel machines for a much wider scientific community.
And we also saw specialized chips playing a role.
Definitely. We mentioned DSPs emerging as sort of low-cost, specialized supercomputers for signal processing. And critically, systolic arrays and other early parallel architectures can be regarded as direct conceptual predecessors to today's GPUs, which are now absolutely essential components, not just in modern supercomputers, but also as the key enablers for the AI revolution.
So the journey from those room-sized machines, calculating artillery tables or breaking codes, to the multi-core processors in your pocket, or the massive GPU clusters training AI today. It's a direct and traceable lineage, isn't it?
Absolutely. The principles learned, the successes, the failures, the architectural trade-offs discovered over decades of supercomputing development, they are still guiding the design of the next generation of computing hardware and software at all scales.
The echoes of Colossus, ENIAC, the CDC 6600, the Cray 1, they're very much present in the chips being designed today, as engineers grapple with those same fundamental challenges of speed, scale, communication, power efficiency, and programmability, just at vastly different technological levels.
Couldn't agree more. The history informs the future.
What an incredible ride that was. We've really traveled from those rudimentary, room-filling vacuum tube machines calculating artillery tables through the iconic vector era into the complexities of massive parallelism, right up to these global networks of processors simulating incredibly complex physical phenomena and driving the frontiers of artificial intelligence.
It truly highlights this relentless, ingenious, decades-long pursuit of speed and computational capability that has defined the field of supercomputing, a constant pushing of boundaries.
Absolutely. So given where we've ended up, with parallelism now truly mainstream, multiple processors on pretty much every chip, and this vision, maybe reality, of the world's computers becoming one giant cluster via the cloud, how does the very definition of a supercomputer continue to evolve from here?
That's the million-dollar question, isn't it? Or maybe $1 trillion now.
Right. What will truly differentiate the world's fastest machine in, say, 10 or 20 years? When sophisticated parallel processing is just ubiquitous, will it still be just about raw processing power, about LinPack performance?
It seems unlikely to be just that. Perhaps the definition will shift further, maybe towards measuring the ability to solve specific grand challenge scientific problems faster or with higher fidelity, or maybe efficiency becomes paramount performance per watt, sustainable computing.
Or maybe new types of computation.
Exactly. Will it be about the ability to handle entirely new computational paradigms seamlessly? Integrating quantum computing capabilities, perhaps, or neuromorphic computing that mimics the brain, or maybe even the effortless integration of biological and silicon systems, pushing the boundaries of what computation even means.
That's the provocative thought to leave everyone with, isn't it? What new metrics, what new challenges will emerge as we strive for even greater computational feats beyond just FLPS? Will it be about data movement, AI integration, energy security, programmability?
All of the above, probably. We encourage you, the listener, to ponder these questions. Maybe go visit www.top500.org yourself, browse the list, see the trends, but always keep Amdahl's law and the limitations of benchmarks like LINPACK in the back of your mind as you explore the cutting edge.
It's a field that's constantly reinventing itself. Thank you so much for joining us on this deep dive.
My pleasure. It was fascinating to revisit this history.